Hi everyone, I'm extremely delighted to welcome you to today's session on Rethinking Functional Safety for Software Defined Vehicles. I'm Parul Agarwal, Senior Manager at MOSCHIP and TUV Certification in Functional Safety. I'll be co-presenting the session alongside my colleague Rohita Gupta. Rohita, Rohita is a Senior Manager and also a TUV Certified Senior Functional Safety Consultant at MOSCHIP.
Hello, everyone.
Together, we will be taking turns and walking you through this one of the most important challenge functional safety is facing in automotive industry. During the session, if you have any questions, please share in the comment section and we will address them at the end of the session. Let's start with a simple but powerful scenario. You plug in your EV, head to the bed, and while you're asleep, it quietly it quietly does a software update. Next morning, the lane changing assist behaves differently because of the change in code overnight. Now, here's the question for you. Do you still trust the vehicle in the same way you did yesterday? That split second doubt in your mind captures the new reality of software defined mobility. With that thought in mind, let's jump into what we'll be covering today. We'll start by introducing MOSCHIP, then we'll take a fresh look at what is software defined vehicle, that is SDV, what is functional safety, that is FuSa. We will understand what challenges FuSa is facing with SDVs. Next, we will share some real world implementations and how we have addressed them, including a technical view of forward collision warning system. We'll also offer a future facing perspective on the possibilities of AI, Edge AI, Gen AI, or Agentic AI for FuSa. Finally, we will discuss MOSCHIP capabilities in automotive domain. By the end of the session, you'll understand why traditional functional safety falls short for software-defined vehicles and gain some real-world insights to future-proof your safety strategy. A quick introduction of MOSCHIP for those who don't know us. MOSCHIP is a publicly listed engineering services company with over 25 years of silicon to software DNA. From silicon to systems to software and safety, we cover the entire product lifecycle, all the way from idea to prototyping to production and sustenance. Our work spans from designing ASIC chips and custom SoCs to building hardware boards and embedded software, from HMI and connectivity to AI and Gen AI based solutions. We also bring deep experience in edge AI, cloud integration, vehicle to everything that is V2X, predictive maintenance, and cybersecurity. Now let's go back to that earlier thought. Your car is behaving differently after a software update. And take it a step further with a quick story of two different cars. Back in 2010, a good friend of mine bought a trusty compact sedan, solid steel, mechanical steering, a handful of ECUs doing their own jobs. Once it left the factory, its behavior never really changed. Brakes braked, airbags deployed, end of the story. Now jump ahead in 2025. The same friend now drives an electric SUV that centers itself in the lane, tunes regenerative braking to her style, and downloads software while she is asleep. Now, one morning, after a routine overnight patch, she presses the start button and nothing. No warning light, no rattle, just silence. A hidden dependency in the update tripped a validation check and powertrain locked itself out. This wasn't a hardware failure. It was caused by a few lines of code. And that's what brings us to the crucial questions. And I'd like you to keep in mind for the rest of the session. Can a framework designed for isolated ECUs still protect a vehicle that rewrites its own software every night? That is exactly why we need to rethink and re-architect functional safety for a software-defined era. In the next section, we'll unpack what makes this new vehicles stick and why traditional ISO 26262 approaches start to fall short. First, what are software-defined vehicles? So today's vehicles are not just machines anymore. They are computer on wheels. Software defined vehicles or SDV is a vehicle whose core capabilities from driving functions to infotainment to safety are primarily controlled, enhanced and updated by software rather than a fixed hardware. Let's look at some of the defining characteristics of software defined vehicles. Firstly, it has centralized computing architecture. So instead of relying on multiple ECUs, that is electronic control units, as in traditional vehicles, SDVs centralize computation in domain controllers or high performance compute platforms. It has over the air updates, unlike traditional cars where functionality is largely locked at manufacturing. SDVs are dynamic platforms that evolve over time via over the air software updates, very similar to how our smartphones gets updates. It has cloud and AI integration, which does real-time data processing and AI-driven decisions which enhance performance. Next is continuous integration and deployment. SDVs use cloud-based CI/CD pipelines and simulation-driven validation to safely deliver software updates. And lastly, they have security from the day one. As we see, software defined vehicles heavily rely on connectivity and code, which makes it essential to have robust end to end cybersecurity to protect against hacks, breaches, or any unsafe behavior. I'm sure this gives you an overview of SDV. Now, next, let's understand a bit on functional safety and ISO 26262. When we talk of functional safety, first question that comes to mind is why does functional safety matter at all? Let's look into that. Firstly, it reduces failures. Data has shown that vehicles with robust functional safety, that is FuSa implementations, see up to 50% drop in safety critical faults. So that's not just compliance, that's the real world impact. Secondly, it mitigates collision risks. Especially in ADAS systems, well architectured safety logic can reduce collision probability by 30 to 40%, even in complex sensor environments. And thirdly, it obviously builds customer confidence. A recent study shows that nearly 70% of the customers prefer brands that can demonstrably manage software and sensor failure gracefully. So, safety is something that must be designed into the architecture, not something which we can add later. Now, let's see how functional safety evolved over time in automotive. In the earliest days, everything was mechanical: cables, levers, thick steel. If a part failed, the driver compensated, and that was considered good enough. Then electronics crept in during 1980s. Suddenly, we had anti-lock brakes, airbag inflators, run by tiny microcontrollers. Each company invented its own rules. So most fixes were reactive. A fault appeared in the field, engineers patched in, and life just moved on. Then in 2011 arrived ISO 26262, which gave everyone a common playbook. Now words like HARA, SL, redundancy, traceability meant the same thing worldwide. And safety became a discipline you planned for instead of an emergency that you cleaned up later. Then few years later, cameras, radars, partial autonomy showed up. Software now, not the driver's foot, started deciding when to steer or brake. Functional safety stretched to cover complex sensor fusion and dozens of distributed controllers talking at millisecond speed. Today, the vehicle is essentially a rolling cloud node. AI models update overnight, connectivity never sleeps, and security bugs can cascade into safety incidents in real time. We are no longer protecting components from failure. We are protecting dynamic learning software from itself and from the outside world. So we can see the shift here from traditional automotive safety to SDV ready safety. Static, hardware defined, and isolated approaches have given way to dynamic, software driven, and virtualized methods. Safety is no longer fixed or standalone. It's continuously verified, shares compute, and must be co engineered with security in real time. So, up to this point, we've seen why functional safety matters and how it has evolved. Now, let's talk about what it actually looks like in day to day engineering and where ISO 26262 fits in. Now, functional safety is basically the car's what if reflex. So, it keeps asking if an electronic part or line of code misbehaves, can the vehicle still keep everyone safe? That question feeds a repeatable four-step loop. First is hazard analysis and risk assessment, which starts by listing every credible mishap and rate each one for how severe it could be, how often it might happen, and how easy it is to control. Next is SL assignment. Based on the risk, we assign a safety level from QM up to SLD. The higher the grade, the tougher the process. After SL, we define safety goals and mechanism, which decide exactly how the system must behave to stay safe. Then comes the implementation and validation, where we build the hardware and software, through every test and fault injection you can think of to prove the system works well under stress. Equally important are safety analysis activities here, which start with high level vehicle hazards and drills all the way down to line by line code reviews and FMEA DAs. On silicon, so the concept, system, hardware, and hard software teams, they all stay in sync. At Moschip, we accompany customers through the entire journey planning, analysis, architecture, tool qualification, and finally post launch validation. So, safety isn't a patch, it's properly baked into the product DNA. Keep the rhythm of this four-step loop in mind. On the next slide, we'll see more details on two critical steps of HARA and SL. HARA. So HARA basically stands for Hazard Analysis and Risk Assessment. It's like asking what could go wrong and how risky it is. We do this by looking at each possible failure in the system and scoring it in three simple ways. First is severity. That is, if something goes wrong, how bad it could be. Like, can it be a minor inconvenience or a serious accident? Next is exposure. How often could this happen on the road? Last is controllability, which raises the question if it happens, can the driver or system avoid danger? So, in a system, all hazards are identified and scored on all three parameters. So, after the scoring is done, SL, that is automotive safety integrity level, that comes into picture. It's like what is the danger level of the risk? This ranges from QM, that is quality managed, to SLD. So QM means it's a non-safety critical. SLA means low safety risk, SLB and C moderate risk, and SLD is highest safety risk which needs the most safeguards. So here the important part is the SL level determines the depth of your safety activities. That is, it tells how seriously we need to treat each one. Based on that, safety activities are determined from architectural requirements to verification coverage, tool qualification, and independence in assessment. If we talk at ASIC level, here also, as the SL level increases, the demand on the ASIC grows from adding simple diagnostic at SLA to full fault tolerance, redundancy, ECC, safety monitors, and watchdogs at SLD. We at Mostep Must chip engineer ASICs with safety mechanisms proportionate to SL requirements and have delivered silicon platforms validated to SLD with full FMEA, DFMEA, and toolchain compliance. So by now, we all must have got some idea on how SDVs are posing challenges for traditional FUSA. So let's bring everything together and summarize the key challenges here and how it is impacting functional safety. SDVs have dynamic software updates, and ISO 26262 is rooted in the V model, and it wasn't designed for continuous deployment or field updates. Any change might affect existing mechanisms, invalidating previous safety validations. SDVs use AI/ML in safety functions, and in traditional FUSA, safety validations become hard due to lack of determinism and formal proofs. Next, SDVs have service oriented architectures, and critical functions may rely on services that are not guaranteed to be available, breaking assumptions of fail safe design. ISO 262 is based on static tightly coupled systems. It doesn't yet support safety assurance in loosely coupled runtime service environments. Next, we have mixed criticality on shared hardware. That is, modern SOCs in SDV often run both QM, the quality managed, and the SL level software together. And an error in a QM component, for example, infotainment, may affect safety critical timing or memory used by systems like forward collision warning or braking. So it becomes a challenge. Then there is interdependency between cybersecurity and safety. Data corruption from cyber attacks may cause undetected safety faults. Also, SDVs have frequent software releases and agile methods. And rapid iteration may skip or delay safety analysis, leading to incomplete safety cases. So, as you can see, the traditional functional safety landscape is being pushed to its limits by the dynamic software driven nature of SDVs. That's why we need to rethink our safety strategies. And my colleague Rohita is going to walk you through this with the help of one of our project use case as to how we can mitigate these challenges. Handing over to Rohita.
Thank you, Parul, for the insightful session on functional safety and SDV. Good morning, everyone. Good afternoon to all, and good evening to the ones to all. Let's ground the safety ideas we have been discussing in a real day-to-day feature, forward collision warning or FCW. Picture yourself driving Picture yourself driving high speed on a busy expressway. Traffic ahead slows suddenly. In a conventional car, the driver alone must sense, decide, and react in about half a second. In today's vehicles, a digital co pilot is constantly monitoring, analyzing distance, speed, and driver inputs. If the math says impact is coming, the system flashes a warning on the screen, sounds an alarm, or even gently applies the brakes. In short, FCW shows how modern vehicles share the workload with the driver. In next few slides, we'll talk about forward collision warning system in ADAS controller project, which we did for one of our customers. And with the help of that, we will see how we mitigated some of the SDV challenges. Next is not. This project was for a Taiwan client. Here, our Moship team was closely engaged in implementing functional safety, designing and developing software modules, integrating artificial intelligence and machine learning algorithms for an ADAS controller. Moship team architected this system with camera, LiDAR, and radar sensor data for environment perception. As a part of this ADAS controller, forward collision warning is one of the advanced driver assisting feature which we will be discussing today. For semi-autonomous or fully autonomous vehicles, FCW is integrated with features like automatic emergency braking or steering assistance for added safety. Being a critical safety feature, it is targeted to comply ASIL C. Let's take a closer look at the functional and technical overview of the forward collision warning system and a few of the key functional safety challenges we faced in the project. The layout that you see shows the key components of forward collision warning system. Sensor data acquisition, data processing and fusion, intercomponent communication, an ADAS service for decision making, and a human machine interface to deliver driver alerts. If we connect these blocks together, this is how flow looks like. Sensors capture the data, which is cleaned, pre-processed, and fused. Encrypted data is transferred through communication channels to ADAS controllers. We have designed an AI ML based FCW algorithm that processes sensor data for object detection and collision estimation. For systems reliability and fault tolerance, everything safety critical travels on redundant and diverse paths, both in sensing and in communication. Cameras, radar, and LiDAR watch the same road from a different angle, while dual channel CAN and Ethernet move the bits. Think about a winter night when the snow starts coming hard. LiDAR signals bounce off falling snow, which causes false or noisy reflections. The controller spots confidence dropping and flags the sensors as unreliable. Instead of shutting down the software, it adjusts the thresholds and runs on camera plus radar alone. The car still flashes a warning icon and pings the driver, but it also pops a message LiDAR sensor visibility reduced. In other words, the system degrades gracefully, not fatally. It's not the faults are limited to sensors only. A loose pin can disconnect the primary CAN bus. That's why every life critical message writes a dual channel. While redundancy is commonly used safety mechanism for handling failures, it is not always the best or only solution. Redundancy adds cost and design complexity, and it's typically reserved for safety critical systems. Moreover, redundancy do not cover all types of failures. It primarily resolves single point failures. So we stack other defenses on top, like end-to-end communication protection is used to detect corrupted, lost, and delayed messages through cyclic redundancy checks, sequence counters, timeout detections, and message authentications. Functional monitoring to monitor health of the software and hardware at runtime through watchdogs, runtime checks, and built-in self-test. ASIL partitioning and freedom from interference is required to prevent lower ASIL software corrupting higher ASIL safety functions. Timing supervision is done to detect overloads, hangs, or missed deadlines. OTA update safety is required to ensure update doesn't violate safety goal or introduce faults. There are plenty more, but you get the idea. Combination of redundancy, monitoring, and smart degradation is how we keep FCW system functional when the weather, the network, or the latest patch try to trip it up. Inside a software-defined vehicle, a forward collision warning stack lives at crossroads of six tension points, and each box on the slide captures one of them. Let's start with dynamic OTA updates. Code shifts weekly, sometimes daily, so every patch has to go through structured and defined safety process from impact and hazard analysis to verification and validation. If after the update, field logs show false breaking, we flip back to the last stable version. Next is AI in safety functions. AI-based object classification may misclassify or miss obstacles, especially in edge cases. A neural net is brilliant until fog or glare drops its confidence. We wrap it with confidence estimators and safety monitors. Next in the row is service-oriented architectures. Collision logic relies on microservices that might time out or reboot. If a service fails, FCW degrades gracefully to basic brake alerts instead of going dark. Next is mixed criticality on shared hardware. In modern software defined vehicles, it's common for safety critical and non safety critical systems to run together on system. For example, a forward collision warning system may operate alongside a non safety critical infotainment system. An unisolated system can affect the functionality of the safety critical system. If the infotainment system crashes or uses too much CPU or memory, the FCW system might not get resources it needs, affecting its real time performance. Subsystems are commonly isolated using virtualization technologies such as virtual machines, containers, or hypervisors. Also, dedicated real time cores or hardware partitions are assigned exclusively to these tasks. Next is cybersecurity and functional safety. They are now twins. Sensor data tampering can mislead FCW logic. So, our sensor frames carry CRCs, counters, and authorization tags. Finally, frequent software releases and agile methods keep everything moving. Automated safety regressions, update approval gates, and post deployment analytics close the loop so each update renews the safety contract instead of freeing it. To address these challenges, functional safety in SDVs must go beyond traditional methods and adopt an integrated approach of combining safety, security, and functionality. This ensures that SDVs remain safe, secure, and reliable, not just at the launch, but throughout their entire operational life cycle, and even as they evolve with new software and connected capabilities. Functional safety in SDVs is dynamic, continuous, and adaptive. Now, I would like to highlight some of the key projects in automotive domain which were executed by Moship team for FuSa and cybersecurity. One of the projects that we did is cyber secured keyless vehicle access system. For one of the automotive giant, team developed a keyless access system via Android app. The system is designed with strong authentication, cloud-based dynamic key management, and real-time credential validation for safe and secure access. One of the major challenges was managing the dynamic lifecycle of the digital keys across multiple platforms and vehicle models. Another significant challenge was end-to-end encryption over Bluetooth low energy, maintaining the low latency. This is another project which is ASIL-D compliant sensor data processing software library. For a Taiwan customer, we developed a optimized software library to process data from camera, LiDAR, and radar sensors. This ASIL-D compliant library targets applications in robotics, drones, and autonomous vehicles. For compliance with ISO 26262, it is developed as a safety element out of context, SEOOC. As with any SEOOC, it was crucial to precisely define the assumptions of use and assumed safety goals, even without knowing the exact system context in which the library would eventually be deployed. At the same time, it was critical to validate the software under different configurable parameters. Our team has been a key contributor for the ASIL-D compliance. This is another ASIL-D case study in which we developed automotive firmware for an SoC. It is fully aligned with functional safety and cybersecurity standards. The firmware included key features such as secure boot, encryption, OTA updates, and advanced power management. The main challenge was to balance the performance with stringent safety and security requirements within the limited resources. Next, we have FuSa compliant in vehicle HVAC system. We developed an ISO 26262 compliant in vehicle climate monitoring system that tracks cabin temperature and humidity in real time. It connects with HVAC system and securely sends data to the cloud for remote monitoring and diagnostics. Major achievements of the project were real-time edge processing with under 100 millisecond latency and secure data transmission into OEM's remote diagnostics and analytics platform. Last but not the least, we have FuSa management for Semicon IP. For one of the Semicon IP leader, we have established the functional safety concept for CAN FD and PCI Express. We also established the functional safety processes guidelines for semiconductors, software, and hardware as per ASPICE and ISO 26262. We defined a custom workflow to bridge the gap between functional safety lifecycle and process maturity model. To explore how cutting edge technologies like AI, generative AI, and automation can help address these FUSA challenges in SDVs, I now call upon Parul to share her insights.
Thanks, Rohita, for the insightful case studies. So, as we talk about various challenges, let's take a look at how futuristic technologies can help with safety. Generative AI or Gen AI, interestingly, can help making cars safe too, especially SDVs, which heavily rely on software. Here's a brief on how it can help. Firstly, it can help with auto creating safety documents. Instead of people writing every safety report by hand, AI can help generate documents like FMEA and HARA automatically. This saves time and avoids any human errors. It can also boost test coverage. AI can create edge case scenarios of failures that are hard to find in real life. This means we can test more possibilities and make cars safer. It also helps to keep the traceability sharp. As software evolves rapidly, AI helps maintain accurate traceability and documentation, making sure every change stays aligned with the safety standards. Next, we have virtual testing with digital twins. So, AI can create a virtual copy of the vehicle system to test it safely in a computer before trying it on the road. This will help to catch failures earlier. So, generative AI isn't perfect on its own. It needs human experts to check and guide. But when used well, it makes the safety process faster, smarter, and more scalable. So, here's a view of Moschip's Gen AIoT Cognitive Intelligence Accelerator Suite, which we have been investing as an organization. What you see here is a tailored view of STV automotive applications and safety critical systems. You can see here the Edge Intelligence module. It consists of some of the pre-trained models that enable on-device AI capabilities, bringing intelligence closer to where data is generated. Then we have automation bots, and the bots mentioned here help streamline development and processes in FuSa projects. So key ones included are code standardization bots, regression bots, and test-centric reporting bots. Next, the generative AI brings intelligent content creation and interaction to the forefront. This will help immensely speed up content generation at various stages in FuSa and help engineers, developers, and auditors. Finally, the Agentic AI section showcases Agentic SafeBot and Agentic mechanic developed for automotive and SDVs. Let's talk on the Agentic SafeBot. So it is an AI-powered assistant built to support functional safety teams. It uses advanced language models to understand and navigate complex safety documents and even works through voice commands. So what it can do? Basically, you can ask anything. Instantly, it will answer the question like which SL is FCW tagged under. So it will let you know the answer. It supports document linking. It automatically connects details across HARA, FSR, TSR, that is functional safety requirements and technical safety requirements for better traceability. It supports reasoning, which helps with hazard assessments and decision making. So the bottom line here is that agentic SafeBot is like a digital FuSa expert, making safety faster, smarter, and more connected. Now I would like to quickly walk through Moschip's automotive and FuSa capabilities. This is the visual map out of a modern vehicle, and around it you'll see three core domains where we actively contribute. Starting from infotainment and personalization, we work on HMI design, Android, Linux based head units, and Gen AI powered personalization features that are platform agnostic and production ready. In ADAS and autonomous driving, our teams develop algorithms, multi sensor fusion frameworks, and fail operational middleware layers. At platform level, we provide semiconductor and hardware solutions from auto-grade ASICs to board validation and sensor integration, with safety and power awareness built in from design time. Then on the software side, we support platform and software services, including hypervisor-enabled architecture, middleware development, and OTA update frameworks that are for safety and security. On the IoT and integration and connectivity, we build secure V2X communication layers, telematic stacks, and cloud to edge diagnostic pipelines. Then there's safety, maintenance, and compliance. Our work spans HARA, SL decomposition, safety work products, predictive diagnostics, and audit readiness across the V cycle. If we talk about our functional safety offerings, it spans the entire ISO 26262 life cycle with structured approach to both design time and runtime assurance. We begin with safety concepts, defining the item, running HARA, assigning SLs, formulating safety goals and requirements across functional safety concepts, functional safety requirements, and technical safety requirements. Next comes safety analysis, where we run system level FTA, FMEA, analyze both hardware and software safety mechanisms, and calculate architectural metrics and diagnostic coverage. In parallel, we support SEOOC development, enabling hardware and software to be reused safely across platforms with a detailed safety manual. We then focus on verification and validation using static and dynamic analysis tools like LDRA and performing integration testing with full coverage for MCDC and statement level requirements. And for every critical tool chain, we offer tool qualification, ensuring your development tool meets ISO 26262 confidence levels. And to close the loop, we run audits and assessments, conduct gap analysis, support third party confirmation reviews for safety case readiness. So, from concept to compliance, we engineer safety into your platform. So, from FuSa perspective, the V cycle is where safety is engineered in every layer. And this is where Moschip operates end to end. On the left, we drive the traceability from system requirements to software architecture using tools like DOORS, Confluence, Enterprise Architect to ensure ASIC level rigor. In implementation, our teams developed safety critical code, HMIs with platforms like Qt, Kanzi, CGI Studio, all aligned with model based design principles. And on the right, you see we execute structure verification from software integration to system qualification using toolchains like Vector, ETAS, Google Test to meet ISO 26262 test coverage and independence needs. So, as we see, functional safety is no longer just about compliance, it's about confidence in motion. With the rise of software defined architectures, AI driven functions, over the air updates, safety must evolve. That's why safety today is about shifting left, that is, embedding safety thinking into design, requirements, and system architecture. At the same time, it's extending right, that is, ensuring post deployment safety through runtime supervision, OTA fault recovery, and AI accountability. At the same time, there are standards coming like ISO 26262 third edition, which is also coming. It's yet to come. SOTEF UL 4600, ISO 8800. All these are reshaping how we define and assure safety, especially in the context of AI and autonomy. And Moschip enables this transformation with end to end capability, from concept safety analysis to production ready platforms with built in diagnostics. We have proven experience in safety architecture, software validation, and embedded design. We have experience in integration of runtime monitoring, OTA safety strategies, and AI safety checks. So, with experience across the functional safety, embedded AI, cybersecurity, real time software architectures, we don't just understand the standards, we build the systems that prove them. So, in the software defined world, safety isn't a checklist, it's a mindset. Thank you all for your time and engagement today.